Hello everyone! Today we're going to do mobile price classification on Kaggle, and we're going to use Pytorch for this. And the task here is to classify mobile price range. So let's real quick about the context of the data. So Bob has started his own mobile company. He wants to give tough fight to big companies like Apple, Samsung, etc. He doesn't know how to estimate price of mobiles his company creates. In this competitive mobile phone market, you can't simply assume things. To solve this problem, he collects sales data of mobile phones of various companies. Bob wants to find out some relation between features of a mobile phone like RAM, internal memory, and so on, and its selling price. But he doesn't have, he's not good at machine learning, and this is where we come in, and he needs our help to solve this problem. In this problem, you don't have to predict actual price, but a price range indicating how high the price is. Okay, so real quick, we can see that we have a trained data set and a test data set. We have 21 columns, and let's jump right into the notebook and begin. Okay, libseaborn Plotly, just in case. This is the trained data frame and the test data frame. The trained CSV, test CSV. Here I'm showing the shape of the data sets and also the first 5 rows for each of one of them. So let's just run it, and then we see that the trained shape is 2,000 rows and 21 columns. The test shape is 1,000 rows and 21 columns. We have to remove one column here from the test, which is called the ID, which is just the indexes. Okay. Let's do descriptive statistics, and we'll only analyze trained data set because we believe that we don't have the test data set yet, right? This is what we want to predict. So we'll assume that we only have the trained data set for now. So we're using the trained DF, and we're going to include all the columns in the descriptive statistics. And we can see that they all have numbers. We don't have any text. Okay, it's just, this is going to be easier for us. Okay, so we have battery power, we have Bluetooth, yes or no, and we can also see here by the maximum, clock speed, and so on. We can here, I would say, focus on looking if there are like very extreme values, high extreme values in these columns. For example, if the median or the average is 1,200 or one, yeah. Let's see, look at the max, look at the 75 percentile, if they are if the numbers differ by much. So maybe we have some extreme values here. I'm not sure we do have something here. This data set looks pretty much nice. Okay, this is great. And here's the price range. It starts from 0, the minimum, and the maximum value is 3. We know it's a categorical variable, so we have 4 categories of 4 price ranges. I also ran the train info to see that we have everything integers and floats. Okay, great. I'm checking the missing values, if there is any. No, nothing. Everything is zeros. I can always, let me take a quick look. No, it's all zeros. Okay, now let's start to plot it using our EDA skills. Okay, first let's take a look on the target variable, price range. We see that the data set is pretty much balanced, and most price ranges, most groups have around 500 in each group. Very good for us. We don't deal with any unbalanced data set. Okay, great. Let's take a look at the categorical features. So the categorical features in this case are mostly Boolean features like 0 or 1. So we have the blue, yes or no, dual SIM card, yes or no, Wi-Fi, yes or no, and so on. And here we plot it, and we plot it also near the, we do count plot of Bluetooth, for example. We see that it's balanced between 0 and 1, and we also plot it against the price range. So if you focus on one of them, one of the distributions, and let's say the one when Bluetooth is equal to 1, we see that the price range of 3, I mean the most expensive group, has a little bit more, a higher percentage of with Bluetooth, phones with Bluetooth. Okay, so this is how we can look at it, but mostly the differences are very, very slim, and maybe not even statistically significant, right? This is something else that we can check, but another time. We can also check it for each one of the categories. We see the differences are very, very low. And again, let's take a look. I don't see anything particular interest in the categorical groups. And if we don't see very great differences between the groups against the price range. Okay, so analysis of numerical features. Okay, now we're going to the numerical features and we plot all the variables that are not in the categorical feature group, and also we not plot the price range. So here we have the distributions. Okay, for example, here distribution of clock speed. We can see that there is a difference here. Let's see what else. Okay. This is this is not a continuous variable. This is a discrete. Mobile weight. Okay, and so on and so forth. And this is, okay, we have a right tail here in the pixel height. Pixel width looks like this. Okay. Maybe we can do sound transformation for some of these variables. Maybe a log would help fix this one. But it's not necessary for us at the moment. Okay. Next step is we want to see if we need if we have some multicollinearity correlations between the features, between the predicting features. So we do some heat map with correlations, and we see that there isn't almost no correlations at all between the variables except for two. But this is 0.634 between PC and FC, and we have something pixel height and pixel width. So, but these are not very, very strong correlations. We can ignore it for the moment, but most dataset is not correlated. We can jump to the Pytorch modeling, multi-class classification. So let's go real quick over the models that we're going to use. We're going to use Torch, of course, optimizer, that tensor dataset to prepare the dataset for the data loader. And the data loader is going to split our data into batches for the model. Okay, train test split, we'll see later. We're going to split the train dataset into train and validation. One hot encoder for our target variable. Since we're using multi-class, we have to do one hot encoding. Scaling the dataset, since our features, not all of the features are in the same scale. And classification report to show the predictions. Okay, so this is our X, this is our Y, train df drop price range. Here we're going to use price range. We're going to reshape it into a tensor or a vector of all rows and one column. Encode labels, we're going to encode Y now. We use fit transform. Y is encoded now. We're going to scale the features. Scale equals standard scalar, X scale, transform X, done. Now we're going to convert it into Torch to tensors. So here is the final result for Y tensor for the target variable. As you can see, 0, 1, 0, 0, it's one hot encoder now. Prepared for the model. Split data into train and validation sets. So now we're going to use the X and Y to split it into train and validation. Here it is. I'm splitting it 20% in the test. Now I'm creating the tensor datasets for the train dataset and the validation dataset, and this is how we prepare it for the data loader. And next, data loader, we're going to use train loader and validation loader. We're going to use these tensor datasets earlier, and we're going to split the dataset into batches of 32, sizes of 32. We're going to shuffle the train since we're going to use it for prediction, so we need the randomness. We're not going to use it for the validation loader. And now we build a quick model for Pytorch, a quick Pytorch model, multi-class classification. Let's see, we're going to use sequential. Okay, we're going to use input size, num classes. Input size, how many columns do we have, predictors, and num classes, what is the output, the number of predictions, like for the target. So we have 4, right? We have 4 groups of price ranges, so this is it. It's going to be 4. Okay, we're starting with the input size. The input size should be 20 in this dataset. So we're starting with 20 inputs, and then we're moving to 128 nodes in the hidden layer. We're going to use the activation ReLU. Afterwards, we're going to take the 128 hidden layer nodes and turn it into 64. Use ReLU again, 64 to 32, ReLU again, 32 to 4. Okay, great. We're going to use the forwards, just self-network X, done. Okay, now we're going to initialize the model. So the input size is just the number of columns we have in XTrain. Now our classes yTrain.shape1, we have 4 columns there, it's going to be 4. Model multi-class classification, we're entering the input size in the num classes that we defined here. Loss function, we're going to use the cross entropy loss since it's multi-class classification. Optimizer, we're going to use Adam since it's like, this is the most popular one, so try with this first. Okay, steps of 0.01, collect metrics. Now we're going to collect all this information to later on we're going to plot it. So we're going to use train accuracies, train losses, validation accuracies. Okay, nice ordering. Train loop, I'm just going to use 10 epochs because the dataset is very, very small and it may overfit very, very quickly. So I'm only going to use this. Okay, now we're in the train mode. So this is the training of the model. So let's go over it very quick. For X batch, Y batch, and train loader, it's 32. It's a group of 32 each time. This is the size of the batch. Y pred, this is the model X batch. We get results here. Now we're going to check the results against the Y batch. We're going to get some loss. And then we're going to pass it into the backward pass. We're going to initialize the grads and then gradients, and then we're going to do all the calculate the gradients and everything. Then we update the weights, optimizer.step, and then we just add it to the losses. So we count the losses for each epoch eventually. Okay. Train losses, .append, run loss. Okay. So here I'm just, this is the average loss for the train loss for the epoch, and this is the average train accuracy for this epoch. Model evaluation, all preds, all labels. This is for later. This is where I'm going to show the classification report. Okay, so for now ignore it, but what it's going to do, it's going to do the calculation for each epoch, but eventually the final epoch will show the real results, the final results. So first we're going to use it, this is the evaluation part. So with Pytorch, no grad, for X batch, Y batch, invalidation loader. Okay, now we're going to do the same, but for the validation. Okay, we're going to use the loss function, and we're going to use the validation loss. Okay, great, correct, validation correct. All preds. Okay, this is going to the calculations, but it will be relevant for us only in the final epoch. Append average loss and accuracy for this epoch to the list. This is the final validation losses. This is the average one for each epoch, and this is the and the average accuracy. Okay, great. Print current validation results. Okay. This is the validation results with the train accuracy, train loss, and so on. Okay, let's just plot it. Before it, here is the classification report part. Now we use classification report, all labels, all preds. This is all what we calculated here, but it's getting, if you notice, each epoch that we run, it will be empty again. So it will only be relevant for the final one. So let's just run it here. Okay, here's the results. We have, as you can see from the classification report, we have accuracy of 92%. F1 score for each group is 94, 90, 90, 95. So it does pretty well for each of the metrics, right? So close to 90. So we're doing very well in this regard. As support, we have 105 examples in group 0 for the test, for the validation set, 91 in the group 1, and so on. So this is it. Now let's plot it. We've learned the train losses, the validation losses, and the train accuracies and validation accuracies. So this is what we have over 10 epochs. And as you can see, we're starting, as you can see here, it's starting to be a difference between the validation loss and the training loss. And if we add in more and more epochs, we might see like even the difference even goes bigger. So maybe there is a overfitting. The overfitting is getting larger and larger. We can also see the accuracies here. So it's pretty much close to 1. You see that already the train accuracy already reached 1 at this point, or a few times already. And the validation already reached 90 something percent. We can also see it here in the final one, if I recall. Here it is. The validation accuracy at the end is 92% at epoch 9. Okay, let's do some prediction. Wait, let me see. Okay, I already dropped it, so that's why I got a key error. Okay, so I'm taking the test set, testdf.values. Okay, now for the predicting the test set. Okay, I'm running it, the test set, I'm taking it, and I'm removing the ID column, which is not relevant for us. Right now I got the key error because I already removed it before. And now I'll do the, okay, I'm taking the X test, I'm taking the values only, I'm scaling the X test based on the scalar that I used before on the train dataset. I convert the scale data to Pytorch tensors, as you can see here, torch.tensor, and then I evaluate the model. I'm entering into the evaluation mode since I'm not training anything here. So model evaluation, run the model on the test set with George no grad. Here I'm doing the predictions, and here I only take the argmax, the values of the highest scores, like highest likelihoods. And here it is. And this is the prediction. So this is the first row is predicted to be its price range of 3 and so on. And here I can add this to the test data frame. And now I can see the final picture, let's say it. So here's the price range prediction, 3, 3, 2, 3, 1. And that's it. We are done with the prediction. I hope you enjoyed it, and if you have any questions, please let me know. Thank you.